Hi guys, so today we are solving a very famous problem 01 knapsack. So let's take it to our board, right? So here basically uh, we are given weights and the values of n items, right? We need to put these items in a knapsack of capacity W. So we have a knapsack, basically sack. The its max capacity is W. It's given in the question. Now note that we have only one quantity of each item. Okay, so for example this n is 3, like 3 items are there. The maximum value of knapsack is 4, so this will be 4, and then the values and corresponding value will be as follows. So we will having a values array with values as 1 2 3, and a weight array with values as 4 5 and 1. So right, so we are given this which reminder value is verified, also given an integer w which represents the maximum capacity, right? This is w, this is well the two arrays, and find out the maximum value of subset values such that the sum of the weights of this subset is smaller than or equal to weight w. So the point is, like, we have to put in the values inside this knapsack. So this is our knapsack, so we can put in, for example, this w is 4. So well, how can we put it? So we can put it like uh, value, like weight 4 with value 1, so our max value will be 1, right? Now can we put now the max back capacity, which was w, so this reduced to w minus 4, which is equal to 0, right? So we cannot put any more elements, right? So this is one of the answer, but this is not the most optimized one. So we are given, like, we have to return the maximum value of such that uh, yeah, so we have to return the maximum total value in the knapsack possible. So if we go ahead, right, so we take this out, so again the knapsack is empty, and we decide to put a 5 weight 5. So this one we can't put because its capacity is greater than the knapsack w, which is 4, so we can't put it, right? 5 can't put, so 1. So if we put this one, then the we get in here, so the max value will be 3, right? So we put in 1, but the max value will be equal to 3, and this will be our answer, right? So this is one bit of doing it, like iterating over it, but this will cause a lot of complexity and will not be a most optimized one. So what we can do here, like, using this, we can see that this we have to try out all the combinations, right? So let's take another diagram and take this into our new page as well. So right, so what do we have here? So we have a bag of capacity w, we are given some values array and weight array, and we have to put in these weights such that the max profit is taken out. So let's take a look at the function definition. So this is the function definition, right? So we will be getting this one, right? So we have to return a int. So yeah, so like I was talking earlier, so we have to try out all the possible cases over here. So let's take another example maybe. So this one is all right. There are not much examples, but let's see. So the knapsack that we have to try, right? So let's take how we can approach this. So we are basically having a weight w, right? And we have two choices around it. So first one is, like, if the so this is the small, let's call it wt, right? And the w is the capacity of the knapsack. So if wt is less than equal to w, then only we can proceed with that choice, right? But if the wt is greater than w, then we cannot proceed any further, right? Because if the capacity of the weight is greater than the knapsack itself, then we cannot put this element inside. So but if it is less than equal to, then we have a choice, right? So 01 knapsack, it's called 01 knapsack because we can either include the full item, right, complete item, or don't pick. So here in this example, like this, let's take the weight one. So we have 4, 5, 1. So we have two choices here. We can either pick it or not pick it, pick it or not pick it, pick this or not pick this, right? And after doing all this, we are returning the max value. So now that here it is for sure, like we are not going to pick it, but if this input is valid, for example this one, so we have two choices, like to include this or not include this. So we will write down it here. So here we will include it in the our answer, and here it will not include in the answer. So this diagram is very important. Using this we will be solving it ahead, right? So we need to basically run a recursive function over here. So we have an int knapsack, we are given weight and weight array, values array, as well as n, right? So the base condition in this case will be, so if the n is equal to 0, which means the we don't have any elements, or w equal 0. So we always write the base case with the from the smallest possible input. So we check for the smallest possible input in our base case, right? So if n equal 0 or w equal to 0, then it means that the maximum profit will be 0. So we can simply return 0 from here, right? Else, so if the wt, this wt of n minus 1 is less than equal to w, where w is the maximum capacity of the weight, then we can do a recursive call on the left hand side and the right hand side and return the maximum value of it. So we can return max of recursive calls left. So when we are calling it on the left side, so we are including the element, so that means that its value will be included in our answer. So we will be including value of n minus 1 plus the recursive calls on the left, that will be knapsack. So w will be reduced by w minus wt of n minus 1, and we'll call w value and n minus 1. And similarly on the right hand side we will just call knapsack. So weight will remain same because we are not adding any element, and wt, the value array will also remain same, and we just decrease this, so on the right hand side. And in the else condition, which means like this one, so we just take that element and like just consider that element and move ahead. So this will be exactly similar to this. So this will be knapsack wt val n minus 1. So this will give us the our desired solution. So let me show you the code for it. So here I'm keeping the both the choice diagram as our code for the understanding, and now we can walk through it. So we are basically have a knapsack function with weight w or with the following inputs, and this is the base condition, and if the input is valid, which comes from here, right, is less than equal to w, then we can return the maximum of the uh, if we are including this, so we will add this value and decrease the knapsack weight, and when we are not including it, then this we will call this one on the right hand side. We are just considering the element but not its value or weight. And similarly in the else condition, so this one we are returning the knapsack uh, as we are not considering it, so this is just similar to this. So yeah, that's it for the recursive code here. So but this gives TLE, right? So how can we optimize it? Yeah, so to optimize this further, we will be using DP, and inside DP we will be doing the memoization. So memoization step is the step where we are using some data structure to store the result from our uh, iterations. So if the results was already calculated, then we return it. Otherwise, we call the recursion tree. So what I mean by that is, so for example, this was our recursion tree, right? Something like this. So let's say this is for n minus 3, right? So we already have a result from this as x. Now we don't have to call this for n minus 3 again, right? If we can just return the answer of this, so these many calls will be saved. So n minus 3 will be x, we will just return x from here. So this is how we can optimize it. So let's see where it is possible. So if we look inside our recursive function, so we can see that these are the base condition, right? So we are returning 0. So the thing to note here is, like, wherever we are returning the values, we just store it in our data structure. So we can store it over here, and then a very important step is to, before going into any recursive calls, we check it in our DS, whatever that may be. In our case, this will be a 2D array, right? So we will check it from here, and then again here we will be storing it in our data structure. Here also we will be storing it in our data structure. So wherever the return statements are, we'll be storing it in our data structure first. So here we have the optimized code for here where we are using the memoization. So for this, what we have done is we have created a 2D array DP. So yeah, one question arises, like how to choose DP array. So the main point to note here is, like, we will be always be choosing the DP for the elements for the things that are changing. So if we look at our recursive call, we can see, like, this weight is getting changing, right? This is getting changed and this is getting changed in every recursive call, in every or some recursive or whatever. But in a nutshell, these two values are changing. So we will be creating a DP array of n and w. So we are just keeping it as n plus 1 and w plus 1. So y plus 1, because we are doing one based indexing, right? So this is the, we created a 2D vector DP of size n plus 1, comma So this is visualize this as this. So we define n plus 1 blocks over here. This is 1 0 1 2 3 4 5, right? And in these blocks we are storing an array of size w plus 1. So this is also w plus 1 w plus 1 w plus 1. So this is how it's getting stored. So this is the syntax, it's very important, so please take a note of it. So this is the row, let's mention it somewhere. So this is row, and this one is for column, and this is the value which we are initializing every element, right? So this will be -1 -1 -1, and in the end, so we are basically calling our helper knapsack function, which are taking all those parameters in addition to this dp data structure. So we are passing it by reference, so such that it's not making any duplicates over there. So if we look at our recursive call, so we are returning 0 here. So here we are just storing it in our dp and then returning it, and this is the most important step. So we are basically checking if element already exists. If it does, then we just return the answer from it, and if it doesn't, then we will be calling the recursion. So recursion will be same, and we are just storing the result in our dp of this max whatever value of n minus 1 knapsack blah blah blah, and similarly this, right? And in the end, so this is basically a dp of n cross w. So let's say this was the dp, right? So this is w, this is n, 0 1 2 0 1 2 3. So what this actually depicts is, for example, in this block, 1 comma 1, it it shows the max profit when n is 1 and weight of knapsack is 1. So this is the max weight of knapsack. And similarly for this example, let's say 1 2 3 4 5 1, we will be having this kind of uh, n plus 1 w plus 1. So this will be 0 1 2 3 0 1 2 3, and we will be getting the inside this box we will be having wt and val as wt as uh sorry, maximum weight of knapsack. This is w actually, and val. So w as 3, and val will be of, when we are considering 1 2 3 3 elements, so 3 will be stored here. So yeah, this is the memoization in of dp. Now we will see at the tabulation. So now we are going towards the tabulation part of our solution. So in the tabulation we are also creating a 2D vector. So why 2D vector? Because as explained earlier, so the n and w are changing. So we are basically making we are going to store this in our dp array. So this will be like this. So we are storing the rows as n and w in columns. So these are n and this is w. Please note this is capital W and not the weight array. So capital W is the capacity of knapsack. So here we are declaring our 2D vector, right? So here please note that we are not initializing with anything. So previously in the memoization we were initializing it with -1, but that's not the case here. So yeah, if we so do so it's the initialization in it is quite different. So initialization in tabulation always comes in the first row and column. So this one, these row, right? So these basically will be our initialization. So let's put indexes over here, 0 1 2 3. So let's take any block. So let's take this block, right? So this is 0 comma 2, which means that we have 0 elements and the size of bag is 2. Size of bag or the maximum capacity of where of knapsack is W, which is 2. So what will be the maximum profit in here? Think for a second. Yeah, it's 0. So because we are not having any element, so there is nothing to put in the knapsack, then the maximum profit 0. Similarly it will be for this one 0. And if we look at this column, so we have 0 capacity of knapsack and we have to put 0 elements, so the maximum profit will be 0. If we have to put one element, we can't put it. Two elements we also can't put. Three elements we also can't put. So this whole row will be 0. So this will be initialized as 0 0 0 0 0. So that's what we are doing it in this step. So whenever I is equal to 0 or j is equal to 0, then we are putting zeros over here. So this is the initialization step of our DP. And now we are just calling our helper knapsack function and passing this DP in here. So since we have initialized it, so the main point of tabulation is we are eliminating the recursive call. So when we are going from memoization to tabulation, so here we are elimination of recursive calls. And how can we do that? So if we look at our recursive function, so we are just we basically need to remove this calls, right? So whenever there is a recursion call, so like this is a recursive call, right? This one and this one is another recursive call. So we check like which elements are which parameters are changing. So in this case this n-1 is changing and w this one is also changing, right? And this one is also getting changing. So how to write this is like this. So we are basically initialize our array. Now we are going to fill up for these boxes. So this is I equals to 1 to n and j equals 1 to n. So that's the same thing we have written over. Now since this j is actually uh, the max capacity of knapsack, right? So this is why we are checking it over here like this, like wt of I minus 1. So I minus 1 will be this or this, like we were having I is basically n or element number in array. So we have basically replaced this w with j, right? So wherever there was w we are just putting j. So this is one was also capital W, we have put in j over here. And similarly for the I, so I is basically our n. So in place of n we have put in I and in place of w we have put in j. Now how to convert recursive call into the tabulation one? So we basically write whatever is changing. So this one here we are having a value of n minus 1 plus helper of knapsack. So this will remain the same, and this will remain the same, and this will be our dp of uh so we are doing an n minus 1, right? Sorry, this is the, let me clean this a bit. So this whole is one recursive call, and this one is another recursive call. So this can be rewritten as, so we are changing n, right? So dp of n minus 1, and this will be w minus wt of n minus 1, where now w is our j. This will be j minus wt of n is I minus 1. So this is how we can rewrite this recursive function. And similarly over here, this will be dp of w is not changing, just n is changing, so I minus 1 and j, right? And this will be also dp of I minus 1 j. So this is the same thing that I have written over here. So dp of ij, and yeah, note that we were storing it in nw, but this is now ij, right? Because we are uh, getting answer for this index or whatever. So this will be max of value of I minus 1 plus dp of I minus 1 jw minus t, or this, so this is the left recursive call. So we had this uh, weight, we checked if it's less than w, then we can either put it or not put it, and if this weight was greater than w, then we are not going to put it. So this one is the first if this is if condition, and this one is the else part. So yeah, in the this portion we are not including it, so we are just sending dp of I minus 1 j, and else part is remains the same. So yeah, and in the end we are returning dp of n comma w. So dp of n comma w is this. So this means when we are having all elements and the knapsack size is max according to our question. So yeah, that's all I believe. Yeah, cool. So I hope you understand the approaches, all three approaches, and see you in the next one. So like if you thumbs if you liked it, and subs if you loved it. See you in the next one. Thanks. Bye bye.